Hello and welcome everyone to another session in the DataHour series. We are thrilled to be here with you this evening for a session full of action-packed learning. I'm Abhishek Kumar Singh, part of the data science team at Analytics Vidya. For those who have joined us for the first time, a brief introduction to the DataHour sessions. The DataHour is a series of webinars conducted by Analytics Vidya and led by top industry experts. It's a fun way to understand the concepts of data science from the leading players in the data tech domain. And as the name suggests, it's 1 hour dedicated to data. We are hopeful that these sessions are going to be a great source of enrichment and value adding for our community members. So now on to our session today, which is about hands-on with A/B testing. So A/B testing is a crucial but less talked about component of machine learning deployments, which ensures that we release changes incrementally to get an approximate estimate of the effects of the change before you expose a larger audience to its impact. This data hour will cover why we need A/B testing, how to perform it, and the basic maths behind it. We'll also discuss pitfalls to avoid and some rules of thumb that you can follow. I hope you are excited to attend this data hour with us. Before we kick things off and I hand it over to our beloved speakers, a quick recap of the housekeeping items. We are recording the session and the recording will be available on our YouTube channel. You can find the links in the chat section. Please use the Q&A section for asking any questions that you might have during the session, and we will do our best to answer them as the data hour progresses or towards the end. Lastly, we will share a feedback poll towards the end. You all are requested to kindly fill that up before leaving the session. Coming on to our speakers, in this session of data, we have Mr. Kapil Kumar and Mr. Ravi Kumar with us. Ravi Kumar is a data scientist at CRED, where he currently leads the NLP vertical. He has worked extensively in NLP, deep learning, edge computing, graph neural networks, and large-scale model deployment. He has over 5 years of experience in vertical across the fintech domain. He completed his BTech in CSE from IIT Guwahati. There he co-founded his startup Build Blocks, which helped real estate business with networking and marketplace. You can find the links of our speakers also in the chat section. Coming to our next speaker, Mr. Kapil Kumar, who is a data scientist who works on recommendation and personalization at CRED. Prior to this, he has worked on recommendation, NLP, and speech at Daily Hunt and Josh App and has over 4 years of experience in this field. He completed his BTech in CSE from NIT Delhi. He participated in GSOC twice, where he worked on ML projects with organizations like INCF and OBF. Over to you, Ravi and Kapil. The virtual stage is all yours now.
Good evening, everyone. Thanks for joining us on Friday night. So let me quickly start with the A/B test. We'll start with a very a kind of introduction on the A/B test and some kind of terminology we want to address before we directly go to the hands-on thing. So let's start. So the first thing is, whenever we talk about A/B test, is the very less talk across the industry, even in the courses like in colleges or other places, we don't talk about A/B testing. But A/B test is something like which is widely adopted across the industry, like Google, Facebook, anywhere you'll go, you'll find A/B testing going on. So before going to the what is A/B testing, I just want to address a few points on why A/B testing. Okay. So why A/B testing is basically whenever we are going to launch a feature or product, a product or feature can be a very simple, like changing a color of the button or launching a new kind of a recommendation model in YouTube or Instagram or TikTok, anywhere, right? So what we want to know is if we want to know the gain confidence on the feature what we are releasing and what is the expected thing we can expect from, okay, from the feature itself. So first thing what people look into whenever, if I am going to launch a feature. So what I'll be looking on, what is the CTR I'm getting on that? Like if I'm launching a new recommendation model, how many people are coming and looking into that? Whether users are engaging to that feature or not, whether users are satisfied to that product or not. If let's say you're launching a new kind of feature, obviously, and the feature can be like a buggy kind of, people also use A/B test there to roll out the feature so that for the initial rollout, they come to know, okay, my user engagement is dropping. There is some bug in the feature itself. Let's go and debug that. So people industry or company are using those things. The third part, what is one of the critical things which basically as a data scientist you should understand about is the causal impact. Okay, so what is causal impact is basically is not correlation. Let's say you're seeing a lift in something, you similarly see a lift in another matrix, that becomes a correlation. But if you want to debug that, why this lift has come, what feature actually has basically uh, which features basically contributed to this lift, that becomes the causal impact. Okay, so addressing those things is very important, because if some feature is really important to us, you want to make that feature more prominent to the user. The fourth part is insight generation. People do random A/B testing, not random, I'll say, but with some hypotheses. They do A/B testing just to get the insight of the user. Like for example, uh, in Google Pay, we get rewards, cashback, right? There can be a thing where Google started doing a offers related thing. Instead of giving cashback, they started giving the offers. They must have done the A/B testing there. See how user, instead of getting the cashback, are they really happy with the cashback, with the coupons they are getting for the merchant or something? So this kind of data-driven insights can be generated from that. Okay. The fifth point is the uplift what we're looking. Let's say user engaged to a particular, let's say, recommendation model, but the cost of release of that maintaining the recommendation model is pretty high. Okay. So at the end, we want to, before launching that product to the 100% of the user base, we want to define that, okay, this is the uplift what we'll be getting, let's say 10% uplift of the current CTR, and the cost going to be $1 million for that. So at the end, the high level can decide, okay, whether we want to launch this product to the 100% or not. Okay. So this basically keeps a metric inside, give what is the profit at the end the company will be getting. Okay. One of the famous terms what in every industry people use it is the hippo. Hippo basically is like the people who are basically generally the manager who are getting highest paid, right? High paying jobs, right? They come with a cognitive bias. Okay. And they think like whatever the assumptions will hold true in this current scenario. But if you have the data, why not prove that whether it's really going to work out or not? So that's why people use A/B testing across the industry and widely adopted. So let's move to what is A/B testing. So in general, or in a very layman term, what I'll say is it comparing any two groups, distribution of any two groups. One is the control, that is you've not given any kind of treatment, you've not given the feature list to them. And the another group which has basically seen the feature or the recommendation or whatever the features you're launching, they've got the treatment. So what we want to do is we want to compare those two groups and understand like what actually happening there. Okay. Currently, if you see in Google, Facebook, or Netflix, in any company, there are more than 5,000 of experiment running on any day. Okay, that's how the scale of every experiment has been adapted to other companies. So what they are trying to define with this so many experiments, they want to define the statistical significance of that experiment. That is, with some number, not by just intuition, with some number, they want to say, okay, this is the lift we can get launching this feature. Okay. And the A/B experiment is not new. It is being happened in a very 2 centuries back, like 1835 for a drug trial. So A/B experiment is not nothing new, but yeah, the algorithm, the concept, how we are using it, that has been matured by now. Okay. So there are multiple types of A/B testing right now. One is a sequential, which basically help us in launching new feature, new rollout, step by step. Then there is a bootstrap. Then there is a split. Split is basically where we divide the group into two or n groups. Okay. And then give the treatment 1, treatment 2, treatment 3, and keeping one as a control and defining the lift on that. So in this hands-on, we are just talking about the split thing, and we'll not be covering this pencil and the bootstrap. So before going ahead in the hands-on A/B testing, I just want to uh, explain some few prerequisites, some terms. So be with me. So first thing is the mean, variance, and standard deviation. It's a very pretty basic thing. So mean is simply the average of all the data we have observed. the value. The variance is the spread of the data what we have observed. That is how far it is from the mean. And the standard deviation is simply the root of standard deviation is the root of variance. Then I also want to explain CLT, that is central limit theorem. So basically in central limit theorem, why we use this thing is basically, let's say you are having some unknown distribution. You don't know what that distribution is, and the number of samples there is, let's say, in millions. And you want to define like, okay, what is the average expenditure for that user? Let's say in Facebook, you want to know about what is the average time the user spend in Facebook app. Okay, so how you define those things, right? If you are just given a humongous data and you don't have the capacity or the computational power, so how you'll do that? So what central limit theorem says is like, okay, don't worry, just take a sample of 1,000 users, take their mean and keep simulating that. Okay, let's say 100 times. So what you'll observe that the sample distribution mean will be equivalent to population mean. Okay, and the standard deviation, that is the standard error, that is how different it will be from the sample mean to the population mean can be defined by standard deviation by root of number of size of that sample. And the third interesting part, what we see here is like if the sample size is greater than 30 and you do enough sampling, the normal distribution for the mean, what you'll get will be a normal curve. So here I can show you a simple simulation for that. Okay, so it is a simple simulation for the central limit where we are sampling from a simple unknown distribution basically. Okay, and we are just sampling here, and what we are trying to do is we are first decreasing the number of simulation and also decreasing the sample size here. So if you'll see here, I'm just increasing this. Sorry. Yeah. So if you'll see here, the curve is like having a very high standard deviation and not very matured. But if I'll increase the sample size here, okay, and increase the number of simulation, you can see that our standard deviation is pretty gone down and we have better curve here. So that's what central limit theorem is doing here. So let's go to the next slide, next part. So after CLT, one of the critical things what we have is whenever we do the A/B testing, right, you need to have some kind of a hypothesis. So whatever the feature you're launching it, you have to have some kind of hypothesis, like what kind of effect it will do at the end. And defining hypothesis is not easy. Okay, the industry has grown and defined multiple things to basically capture the impact of that feature. Okay, so defining metrics is very critical. Okay, for the hypothesis, like what kind of metrics you'll be looking for the any feature in general across the industry. People use HEART, okay, for launching any feature, that is happiness, engagement, adoption, retention, task success. What does it mean? Like happiness is basically a proxy for user satisfaction. Okay, engagement is like how user is getting engaged to that feature. Like if the people is coming to that, how many times on a daily level it's using that feature. The adoption is basically the new user who's been exposed to this feature, how likely the person will adopt to that feature. Okay, the retention is basically if the people have used this month, will the people will come back again the next month. Okay, the task success, something like we can define is what is the revenue I'm getting by launching this feature. So this becomes a kind of indicators. If I launch a feature, this kind of indicators can help me understand like, okay, these are the impact what I'm getting it, and we can think about some kind of a hypothesis. Okay, so choosing the right metrics should be very correlated to the treatment. Like if you're looking for let's say a recommendation model, and you're launching a brand new YouTube recommendation model in the homepage. So what you'll be looking is the CTR, the people viewing to some video has been increased by how many times, or has been uplifted by a 5%, 10%, that kind of metrics you'll be looking for. there are multiple pitfalls in that. Okay, so let's say in search, I will give you an example there. Let's say you're building a searching algorithm, okay, for a Bing or Google, and you said like, okay, I'm going to launch a new search engine, and that will increase our CTR in that. Obviously, if the CTR will increase, the revenue for the search engine, that is Bing and Google ad, will keep on increasing. But what you have done is that you have made a paid search engine. Basically, whatever you're searching, the results are coming into second or third page. So basically, you've increased the CTR. The ad revenue will increase for the short period of time, but the user satisfaction is gone for a toss, and your retention will drop. That will be by the next month or after 1 week, right? So that creates a problem. So creating a hypothesis just because of one matrix is not good. Okay. While creating a hypothesis, right, while giving the treatment, we define two types of hypothesis. One is the null hypothesis and one is the alternative hypothesis. So null hypothesis means that there is no effect in the control versus treatment. Let's say in treatment, you have launched some feature. So hypothesis I'm creating is that this group of people and this group of people will behave exactly the same. While in the alternative hypothesis, we say like, okay, there will be some effect, either it can be positive or either it can be negative. Okay. The objective of A/B experiment is to reject the null hypothesis. Okay. So what we define is that whatever the hypothesis we have, they are not same. That's what we're trying to define in the A/B experiment. Okay. So there are a few more terms we want to address. That is the statistical significance. Okay. So what is the statistical significance is like, what we want to observe is the two group, right? We want to find like which one is doing better, right? But we also want to define like being that the community, the users are growing in nature, right? So there can be a chance where you see the uplift just by matter of luck or chance. Okay. So we want to avoid those things. So statistical significance says that whatever we are observing is not by luck, but actually the treatment has made that effect, and we are seeing some uplift in the treatment group. Okay, so we are trying to define here two kind of terms here. One is the p-value, and one is the significance level. So p-value is basically whatever the result we are looking into. Okay, how extreme is the observation when the null hypothesis is true? So what does it mean? Mean is, so what is null hypothesis? Null hypothesis is like there is no change in the group. Okay, so it says like the probability of getting the lift when the conditional probability, that is the null hypothesis is true. Okay, which basically define is whatever the value we are getting. Okay, whatever the values we are getting, that is not by luck, but it's actually the treatment thing what we have observed. The alpha is basically what we say is a kind of a hyperparameter. It's a significance level, which I will cover in the later slide. But p-value is this, okay? And we accept the null hypothesis whenever p-value is less than alpha. And we'll also go to how we calculate the p-value. That will be part of the notebook. With the p-value, right, we have what we said, like, okay, we are going to accept the null hypothesis, okay? But the point is key, whatever treatment you are giving to a particular group, it's not enough to get the number is just not enough. You've got a lift, you are going to launch the product. You also want to know about what the confidence you have for that result, what we are observing. Okay. You want to define a confidence. Okay, I am 95% confident on that. The same result will be observed if I do simulation 100 times. Okay. So first thing is confidence level. It's pretty simple. It's 1 minus alpha. Alpha we know that is statistical level. We just subtract by 1 minus alpha and we get 0.05. That is a confidence level. Okay. So what we do is we wrote it down in the percentage, that is a 95%. So confidence interval says like, okay, I'll explain you with the graph. That will be much easier. So you will see here, right? So we have 95% confidence level. So yeah, so if you see the graph here, okay, it's a normal distribution graph with mu at the center and mu minus standard deviation plus minus standard deviation is the red part. Then mu minus plus minus 2 standard deviation is the blue part, and then the green part. Okay. So when I say 95% confidence, that means if I'm sampling the data, okay, from this normal distribution, I will be getting the data between mu minus 2 standard deviation to mu plus 2 standard deviation. The data will lie between these two range with 95% confidence. Okay, so confidence level becomes 95%, and mu minus 2 standard deviation to mu plus 2 standard deviation becomes the confidence interval for this curve. Okay, so that's what we're trying to define the confidence interval here. That is the mean plus minus 2 into standard deviation. That is the range of values. Okay, and we are 95% confident that whatever the result we're expecting, that will fall between these two range with 95% confidence. Okay, so now the next part comes. Now the next part comes is the errors. So whenever we are modeling something or whenever we are doing some kind of experiment, everything is prone to some kind of error. Okay, in A/B experiment, we define these errors into two parts. One is the type 1 error, which you can see here, and one is the type 2 error, that is here false negative, and type 1 error is the false positive. And here is the alpha, that is the statistical level we have defined before. So what it is the type 1 error. So if you define the type 1 error, what it is, it's a false positive. That means that if you have given the treatment, right? If you've not given the treatment, right? If you have not given the treatment, but still the people have used that. Let's say you have not changed the color, but people is still clicking on that. Okay, that becomes some kind of a false positive. Okay, and that becomes a kind of a error which is merely by luck. Okay, the people have used that feature by luck or by mistake, but actually not by your change. That becomes a type 1 error that we want to avoid. Okay, the type 2 error is basically basically the false negative, which basically define that whatever the treatment you are giving, the people is not onboarding to that. That becomes a kind of type 2 error because it's not coming to that, and we don't care about that. It just helps us in defining the sample size, but type 1 error is very important to us, and we define it as a 0.05. Yeah, in the next graph, I'll just show you or explain you like what is type 1 and type 2 error is actually is. So if you'll see that we have two curves, one is the blue curve and one is the red curve. So blue curve is basically the distribution of the first group which are controlled, and the red is basically the curve which basically got the treatment. It can be anything, right? The type 1 error is basically the part which basically got converted, but it's just by luck they've got converted. And type 2 are those parts which have not got converted, but which has not got converted but has got the treatment. So we don't ignore the type 2, but we need to care about the type 1 error at every moment. So here I'll just show you like how the curve moves in the notebook works. So if you'll see here, we have a significance level of 0.05 here, which we have defined before. We have just a simulation here, that is a control mean. We can change the control mean anytime. Okay, this is a treatment mean which we are seeing the lift off, let's say by 10%. Let's make it as 68. Yeah, 68. If you see the control standard deviation, right? I'm just decreasing it a little bit, increasing it, and treatment standard deviation also increasing it. Okay, and if you see that our size is, so whatever we are observing is basically the random. So basically we can't define here is our treatment is doing better or not. Okay, let me do a simple thing like this, and let me increase the standard deviation here. Treatment standard deviation and this, and let me do that. Yeah. So if you see here, this is okay. Yeah. So if you see here, this is the part where we call it as a type 2 error. And this becomes a type 1 error. If you see the mean here, which is greater than the statistical significance, we call it kind of key. We can accept the alternative hypothesis and reject the null hypothesis. Okay. So I am done. Kapil, you want to go ahead and stop sharing my screen?
Sure. Cool. Yeah. So one more thing, you would like over here is basically the type of experiment that we're going ahead with. So, for example, let's say you want to measure an effect of a drug on a user cohort. Now that drug can affect user positively also and the negatively also. So in that case, what we want to do is we want to measure both extremes of the data. So for example, let's say the mean of the effectiveness of your drug is, let's say, 0.9, and the new drug that you introduced, that is your treatment, if it's performed very badly, it would lie somewhere here, like statistically significant, and we can say that the treatment is not working or it is bad, affecting badly. Similarly, if the treatment is working pretty good, then the effect of that treatment, basically the new effectiveness that we are getting, it would lie somewhere here. So in case of, let's say, a serious experiment where we want to measure both scenarios, basically either it is positive impact or the negative impact, in those cases, what we do is we are going for a two-tailed test. So what two-tailed means is basically we are keeping eye on both extremes of the curve. So even if there is a positive result, we will accept it as an alternate hypothesis. And even if there is a negative result, we'll accept it as an alternate hypothesis. It's just that the definition of alternate hypothesis, whether the result is positive or negative, that will change. But coming on to a different kind of experiment, for example, your company has built a feature and you are mandated to release the feature, or let's say it is pretty sure that you are going to go ahead with the feature, but you just want to measure the impact of that feature. So what you can do is you can go ahead with a one-tailed experiment and just make sure, for example, in this case, you are just making sure that, okay, I have a new feature. Let's say you redesign your homepage, and I'm pretty sure that I'm going to launch it, and there are certain few features that I'm going to launch ahead with it. I just want to test whether if it is performing bad or if it is performing at par with the data. So in this case, we are only looking at the left tail. So basically, these kind of experiment where you are only concerned with one kind of result and the second kind of result doesn't matter. In those cases, you choose a one-tailed test. So basically, how to decide whether you want to choose a one-tailed, two-tailed test? Just take a scenario that, okay, what will I do if there is a positive impact? What will I do if there is a negative impact? What will I do if there is no impact? If your answer for negative impact and no impact is similar, then you are looking for one tail. If your answer for negative impact and positive impact and the no impact is different, then in that case, you're going to go ahead with a two-tailed test. Yeah. So when we're doing an A/B test, one thing that we are looking for is like what is the complete procedure or what is the experiment flow from start of the experiment, launch of the experiment, getting the analysis of the experiment, and making the final decision on top of it. The first step of this experiment flow is the experiment setup. So in the experiment setup, someone comes with a hypothesis. Okay, you build a feature. Let's say you build a recommendation algorithm, and you want to test whether your recommendation algorithm is working better or not, whether it is increasing the CTR or not. So that is your hypothesis. Okay, so your hypothesis would be something like, okay, this feature will increase my metric. Now, the other things that you want to know at the point of experiment setup is what is the statistical significance that you are chasing? What is the false positive rate that you are affected? Like, let's say, for example, by default, usually people use 0.05. So what is the value that you are satisfied with? Then you have to choose the beta value also. So what is the false negative value that you are comfortable with? Then comes the lift that you're trying to observe. So choosing the lift is again very crucial, because sometimes it happens that the lift is so small that it is not feasible to launch a feature. And using all of these things, what you come up with a sample size, basically the minimum number of users that you want to put in each variation, so that at the end of the experiment, you get your result and it is statistically significant. Yeah, someone raised a hand. Question? Okay. Cool. I will move ahead. So the next part of the experiment flow is the experiment launch. In the experiment launch phase, there's not much to do, but you have to make sure that the split that you have defined, okay, that 50% are going in the test bucket and 50% are going in the control bucket. You don't want that a user hops from control bucket to the test bucket. This should not happen. Similarly, it should not happen that there should not be a network effect. For example, you do something, let's say you're sharing a data, and now more and more people are coming to the same post, and now you're interacting more with the data. So that what that makes is it reduces the IID assumptions that we take while launching the experiment. At the post-experiment analysis, we are interested in the p-value. Basically, what is the final p-value that we are getting? What is the lift we are getting? And the confidence interval of that lift. And the last part is decision making. Like at the end of the decision, if you see, like if your lift is significant, or like, do you want to launch this feature? Do you want to re-experiment it? Sometimes it makes sense to like again start the experiment with a much higher significance level. So we'll go talk about all of this. Yeah. Cool. So let's start with a sample problem. Let's say you're working in YouTube, you have developed a new graph-based recommendation algorithm, and you want to test its efficiency. So basically, in this case, what would be a good hypothesis? Okay, a good hypothesis is something that is practical and feasible to test. Like if you make a hypothesis that, okay, I've made this change and now people will be more happier, then there is no practical way to measure that. So you want a hypothesis that is practically and feasibly tested. So for example, some hypothesis can be, okay, if I show this car to user, 10 years down the line, user will take a loan or buy a car. Now it is impractical, like it is not feasible to test this hypothesis. So a hypothesis has to be feasible, practically and commercially. Similarly, in this case, in this problem statement, our null hypothesis would be that introducing the graph-based recommendation algorithm on YouTube homepage won't impact the conversion rate or the CTR. Alternate hypothesis will be just the opposite of it. And okay, if you look at the statement that we are making, introducing graph-based recommendation algorithm on YouTube homepage won't have any impact. We are not talking about positive impact or negative impact. We're talking about any impact. So that means we are concerned with both positive and negative impact. And that's why in this experiment, we are going ahead with a two-tailed experiment. The assumptions that we usually take when we are forming this hypothesis is that all the events are individual, all the events are independent and they're identical. So it should not happen that, for example, let's say there is a feature that user can claim and offer only once. But if you're showing it multiple times, the first time he will claim it, but the next event, he won't claim it. Now, because he has claimed the first time, that event had a consequence on all the future events. That next time you show him, he won't do it. Next time you show it, he won't do it. So you have to make sure that the way you are measuring the hypothesis, that all your events are independent and there is no network effect. Network effect, for example, let's say you're on Facebook, you created a Facebook group and you invited all your friends to, okay, let's play. Now, your event is triggering a loop where your engagement is increasing, and that itself is making you, let's say, come more frequently on the Facebook. So the causal impact of that feature that we're testing won't be measured because there are other scenarios that are coming into the field. Cool. Looking into the metrics, the second part is once you have the hypothesis, you want to measure, okay, so you want to measure your efficiency of your algorithm, but what is the metric you select? In this case, let's say we go ahead with a conversion rate that is proportional. And then there is a concept of guardrail metrics. For example, let's say, although you are launching a new feature and conversion rate is your main criteria, what you don't want to affect is the long-term goals of your company or your organization that are like, let's say, user retention or monetization rate or the engagement overall. For example, let's say there is an algorithm that recommends a lot of clickbait. So your CTR will increase, but the retention will decrease. Like with the time, people will stop coming to your platform. So these are the guardrail metrics that are like the North Star. You don't want to touch them. If they improve, that is better. But if they don't improve, and let's say your conversion rate improves, then also you have to make decision. And more often than not, the decision is that the feature can't go ahead. Cool. So in this setup, let's say we are interested in this experiment where we launch a feature on YouTube. Let's say before launching the feature, our base conversion rate is, let's say, 30%. Like user click 3 videos out of every 10 videos, let's say. And the effect that we want to measure is, let's say, 2%. And this is the 2% effect that I'm talking about is absolute. Basically, we want to see if after introducing the treatment, if the CTR becomes 32% or not. Okay, how do you choose this minimum detectable effect? Like before launching the feature, how do you choose this minimum detectable effect? It depends on, like, is it practically significant? For example, for a big organization like YouTube, even increasing the CTR by 0.1% or 0.001%, it can result in millions of revenue. But for a small organization, 1% increase, if you measure 1% increase in, let's say, CTR, and you roll out your treatment, the result, if you roll out the feature, the cost of rolling out that feature will not be substituted by the revenue that you get. So basically, when you're deciding what should be the minimum detectable effect, it should be statistically and practically significant. When I say practical, it means like it should be feasible. Second, third thing is significance level. Okay, what is the false positive that we are expecting, like that we can accommodate, not expecting, that we can accommodate. So, for example, let's say, for example, there is no change from control to treatment, but 5% of the time it may be possible that the sample that you collected from the distribution, it belongs to the right extreme or the left extreme of the distribution. In that case, what can happen is you can falsely tag, okay, your experiment is working, and you can roll this out. And in that case, what will happen is once you go to prod, you won't get the same result. Power, the fourth thing is power, also called like 1 minus beta, where beta is the false negative rate. Basically, let's say your treatment is actually working, but there are chances, like just like the control curve, similarly, you have a treatment curve, and it may happen that although the mean of your treatment is good enough, like it is beyond the critical level, but when you took that sample out of that population, it may belong to the, let's say, the left extreme of that curve. And in that case, you will falsely say, okay, the experiment didn't work. So what is the percentage of times that you can accommodate that scenario? That is 20%, and the like 1 minus beta that we call this statistical power. In this case, we are selecting it as 0.8. Similarly, the hypothesis type is a two-sided hypothesis, as we discussed earlier. And this is the formula of calculating the sample size that is required to test this hypothesis. Now, we won't go into the deep of how we derive this formula. The brief intro is that this formula is derived based on the power, the conditioning that we put on the power and the significance level. So basically, we have this, okay, we have a treatment, and we are making sure that the value of treatment, the new statistic that we're getting, it should have this much power and it should have this much significance. And we get a condition, and based on that condition, we get this formula. Okay. Now, the interesting thing to look here in this sample size formula is this is the delta, basically the lift that you're expecting. So if your lift, let's say, is 10%, if you decrease the lift by 10 times, your sample size would increase by 100 times. right? So the sample size and your left are inversely proportional. So it is very hard to detect very minor improvement, and they are quadratic, related quadratic in nature. So for detecting the effect 10 times smaller, you will need 100 times more user time. Cool. The next part is the post-experiment analysis. In post-experiment analysis, what we do is we observe three parameters, like what is the observed lift, the other lift that we, before the start of the experiment, sorry, just a second, I will just move to the, want to show you. Yeah, so I want to show you a sample size calculator specifically for this use case. So we have created a sample size calculator for both continuous and proportional metric. In this case, we are only concerned about the proportional metric, basically the CTR metric. So yeah, so basically, if you look at here, our alpha we have set it to 0.05, beta, basically the false negative rate that we are able to accommodate is 0.20. The baseline conversion that we are expecting, or the baseline conversion that is currently there, is 0.3, basically 30%. And the absolute delta that we want to measure is 0.02. And the experiment type we have set to two-tail. So if you see, we get, okay, we need 8 to 86 experiment in this scenario. So as I was mentioning in the formula, if you look closely, if I increase the absolute delta, sample size would decrease. And similarly, if I decrease the delta that I want to measure to very small, the sample size that we need will increase a lot. So for example, for 0.2, we needed 8,000, but for 0.01, we need 38,000. So yeah, so basically, yeah. So these are the values that were mentioned in the slide. For this example, we would need 8 to 86 samples per variation. So let's say we are comparing two the variations, like control versus treatment. We need to double the samples of this. Cool. Yeah. Cool. So let's say we have the sample size, we have run the experiment, we have made sure that no user jump from one bucket to another. We have made sure that IID principles are followed. And let's say we are now at the end of the experiment. And now what to do? How do I confirm that whether my experiment is successful or not? And in that case, there are three metrics that we are concerned with. One is the observed lift, that is the actual lift that we're getting between treatment and control. The second thing is the significance for that lift. Okay, you are saying, let's say 5% improvement is there, but is that significant? For that, we are calculating p-value. And the third thing that we are going to observe is the confidence interval of the lift. Okay. So in the p-value, basically what we are trying to find is, for example, this is my curve. Let's say I randomly sample a value from this curve, and let's say that value belongs to this data point. And what my p-value says is what is the probability of getting a data point which is as extreme or more extreme than the current data point. So the probability is area under the curve, and these are the only extreme events compared to this point. So the p-value would be the area under the curve from this point to the edge of the curve. So this is what we are trying to observe. And yeah, cool. Another thing I want to introduce is the z-score. So what is z-score? So basically, it's a measure of number of standard deviation a data point that is observed is away from the mean. So for example, let's say you have mean of 10 and you have a standard deviation of 5, and let's say you are looking for number, let's say 25. So what you will do is you want to find how many standard deviation away that particular data point is away from your mean. Yeah. So what you do here, let's say you substitute mu by 10, your value is 25, it becomes 15, 15 by standard deviation, which was 5. So what it shows is your data point, let's say the number 25, it is 3 standard deviation away from the mean, and the sign of the z just tell you on the which side. So for example, if the Z is positive, we are going for this side. We're looking at this side. If Z is negative, we are looking at this side. Now, if you see both Z value and the P value that we discussed above, both are concerned with a given data point. For example, let's say we have a data point, let's say here. Cool. Yeah. So for this data point, we can define the P value. What that means is, for this data point, the P value would be the area under the curve from this point to the edge of the curve. And the Z score would be how many standard deviation away this point is from this mean. So basically, Z score and both P value are the two different ways of representing how extreme your observation is. They are just two different ways of observing them. So for example, for a P value of 0.05, you will get a Z score of 1.96. Similarly, for 0.01, you will get a much higher Z score. Third thing that I want to stress on is about the confidence interval. A lot of times people, they just look at the P value, they look at the left, and they decide, okay, let's go ahead with the experiment. That is not a recommended way, because one thing, basically the delta that we are getting from moving from control to treatment, that is again a normal distribution, and that again has a confidence interval. If it is too wide, it means that although your current value, let's say you are for a given experiment, you observe the lift of, let's say, 10%, but if the standard deviation of that lift is too high, then it may happen that when you go to the final stage, when you're launching the feature, you may not get the actual exact treatment effect that you're thinking. Cool. So a confidence interval, basically, confidence interval is a range of values that are more likely to include your population mean with a certain degree of confidence. So for example, if you're looking for a very high confidence, let's say 95% confidence, then the range in which your population mean. Remember, population mean is the mean that you are trying to estimate from these two distributions. So your population mean can lie between that two ranges, and with a given certainty or given confidence level. One point I want to stress is 95%. What 95% confidence level? It doesn't mean that, okay, you ran an experiment, you observe this treatment effect, and then you're saying, okay, there is 95% chance that the actual lift that you will get lies between these two numbers. No. What it means is, let's say if you simulate the same experiment, let's say you ran this experiment 100 times. For each time you created a confidence interval of, let's say, 95%. Then out of those 100 experiments, in 95% of those experiments, the actual population mean will lie within those ranges. So just want to make this clear. And again, confidence interval you have to take the Z score, like what is the value that the Z score that you are getting, and you have to multiply it with the standard deviation. So this way you can find the margin of error, basically like the extreme lower bound and the upper bound of the confidence interval. Cool. Yeah. Cool. So till now, what we have done is we have defined our hypothesis. We have defined our parameters alpha and beta. We have defined our lift that we are trying to measure. And based on that, we have calculated our sample size. Now, let's say the experiment has finished, and now we want to find the actual lift. So in case of the two sample test, basically when we're comparing control and treatment, we usually go ahead with a two sample Z test. What it does is, basically it is very similar to the Z score. So if you look the Z statistic, it tells you how many standard deviation your data point is away. This is the actual observed value, this is the mean, and this is the standard deviation. This formula look a little bit complex, but it is the same thing. It's just that now we are concerned with two distribution, and the actual X, basically the observed effect, it becomes the difference in the mean, basically the difference in control mean and the treatment mean that we are observing. Interestingly, if you see there is a zero here, whereas here we are using the mean, that is the mean data. Why here we have used a 0 here is because when we started the experiment, we started the experiment with the assumption that null hypothesis is true. And what I want to measure is, okay, given the null hypothesis is true, how extreme is this observation? So because our assumption is that the null hypothesis is true, so the mean of both control and treatment, we are treating as same. And that's why when we are subtracting the mean of these two distribution, we are replacing it 0. Coming to the denominator part, again, is the same thing, is a standard deviation, but now because we have two samples, and most often than not, we don't know the population variance. So so to overcome this situation where we don't know the population variance because we just took a sample, what we do is what we call the pooled variance. So basically, what pooled variance is, for pooled variance, let's define a variable called pooled mean. What that means is, let's say x1 is the number of positive events in the control, x2 is the number of positive events in the treatment, and n1 and n2 are the number of samples that are assigned to the control and treatment. So we get the overall average, and this is the variance of the binomial distribution. And basically, we divide it by n1 and n2. So this is the formula. Why we divide it by n1 and n2? Again, because when we are creating a sample mean curve distribution, the actual variable that we call standard error, it's defined as your standard deviation divided by the root of your number. But because in case we are taking a variance, we have just squared this part, so the number becomes p into 1 minus p, that is the pooled variance, divided by n1 plus 1 upon the same thing, and the standard deviation in this case would be the under root of the pooled variance. So this term, we call it, let's say, pooled standard deviation. Great. One assumption, so one assumption that we take when we do a z-test is that we have enough number of samples. Minimum size that is recommended is 30, and the another way to represent those conditions or those assumptions is that if your number of users that are present in your control and the actual proportion or value that you're getting from that control set, if the multiplication of those two are greater than 5, it's just like a rule of thumb to say that okay, I have enough sample size, and if I sample from I have enough sample size, if I bootstrap those samples, create a distribution, then I will get a normal distribution. Again, I will just go ahead in the notebook to show like how we're doing it. Okay, so we have calculated sample size. Yeah, we have calculated sample size. We are saying that we need at least 8,286 samples. So let's simulate this. Yeah. So for example, I've created this function. Basically, what it does is, given the base conversion, the delta, and the number of samples, it will just simulate the data. For example, the base conversion is 0.3, delta we are expecting 0.02, and I've kept number of sample as 10,000 instead of 8,200. Just because it is always better to like overshoot in terms of your sample size instead of undershooting. So let's say we ran experiment, we ran it, let's say 1 more hour, and we are getting, let's say, 10,000 samples. Cool. So this is the data that we are getting. Whether, for example, if this user belonged to treatment or not, this is defined by this column, and whether the user clicked on it. Okay. Once we have simulated this data, if we go ahead and once we have simulated this data, the other conditions that we followed when we started the experiment were: one, alpha. What was the alpha that we selected? It was 0.05. And the second, what kind of experiment we had. Like we had a two-tailed experiment, and the number of samples that we got like after the experiment. So once we do the, for example, post-experiment analysis, let's say we get, okay, the p-value is pretty low. Let's say we were expecting it to 0.05, below 0.05, and it is there. It is below 0.05. The test statistic is the z-score that we talked about. Again, the p-value and test statistic are same way, like different ways of representing the extremism of the observation. And the third part that I want to stress about is what is the delta that we actually got. For example, when we created the when we simulated the data, we asked it to add 0.02% more probability to the treatment set. After the experiment, what we get is that this is the delta that we are getting, and this is the confidence interval of this delta, 95% confidence interval. And looking at this 95% confidence interval is pretty important, because this gives us confidence. Okay, at the worst case, how much lift I can get; at the best case, how much lift I can get. And so basically, this looking at the confidence interval is one of the more important aspects of this. Now let's go to the actual function where we are doing the implementation. And if you look at it, what we are doing here is so again, just like the same formula, what we are doing here is we are calculating the mean of the both control and treatment. We are calculating the pooled variance that I mentioned, and then we are taking a square root of that, and then that is what gives us a pooled standard error. And again, now this is the same thing that we showed in the formula, basically mean treatment by mean control and divided by the standard error. And once we get this value, if it is a two-tailed test, then we get the p-value. You have to multiply it by 2. Reason being, because in a two-tailed test, we are concerned about both the left and right extremes. And similarly, from the p-value, we can move on to z-critical. Basically, z-critical is the critical value for a given alpha that we are testing for. For example, in this case, we are testing for 0.05% alpha. So Z critical in this case would always be 1.96. Okay. Right. So these things we get, and then we are just getting the delta, basically what is the observed impact or improvement that we are expecting, and we are creating the confidence interval on top of it. Okay. Similarly, the confidence interval, the formula that we showed, basically the Z critical value into the pooled standard error. Yeah. So we are getting the same way, like we are adding it when we are trying to look at the positive side of it. We are subtracting when we are looking for the negative side of it. Okay. Once we have this data, we get this all this data, and this is the data that we are more concerned about. Basically, the p-value. So in this case, the p-value that we are observed is 0.0007, which is much lesser than 0.05. And yeah, we should accept this null happen, accept the alternate hypothesis. Cool. Let me move back to, I think, the short on time. We just move ahead. Okay. So in this case, our p-value was like 0.007, much lesser than expected. That was alpha that we set as 0.05. So in this case, we will reject the null hypothesis and we will accept the alternate hypothesis. Cool. Okay, one more technique I want to discuss about is the variance reduction technique. So, okay, why we need a variance reduction? So, and what is variance reduction? Why do we need that? So, for example, let's say for a continuous variable, this is the z-score that we are concerned about, basically the above mentioned formula. So this formula is a proportion, and this is for continuous variables. Let's say the session time a user spent or the amount. So for example, let's take an example of this variable. Cool. This is the z statistic. Okay. What we want to do after the experiment is we want this value as high as possible, because if it is very high, it will cross the significance threshold, and we would be like very confident about the result we are getting, right? So basically, our aim is after the experiment, we want to maximize this, right? If you observe in this formula, this statistic is inversely proportional to the variance. Do someone have any question? Okay. Cool. So this z statistics, it is inversely proportional to the variance this is, let's say, control variance, and this is the treatment variance. These are inversely proportional. So one way to increase the z statistic is if you can find a way to reduce this variance. To reduce this variance, what we have to do is like how can we reduce the variance of our data that we are getting from the user set? We can reduce it using the formulation that, okay, there are some major variables, some minor variables that are affecting the data that we're getting. For example, the treatment data that we're getting, it might be affected by the, let's say, the actual recommendation that you're showing to the people on YouTube. But let's say it might also be affected by the screen that the person is using. Let's say he's using a much wider screen, he can see the content much clearly, and he has a higher chance to click, let's say. Now, this variable, let's say the screen size variable, this is consistent for the user before and after the experiment. But this variable is adding some variance to the calculation. So what we do is, in Cupid reduction technique, we are taking the samples, the same set of users prior to the experiment, same set of users after the experiment, and then we are taking the correlation of that metric, basically the CTR prior to the experiment and CTR post the experiment. Now, because this variable, let's say the screen size variable, it is present in both pre and post experiment, we can find a correlation between these metrics and use that correlation to reduce the effect of this additional variable. So all we are doing here is we are reducing the variance here, and that will help us increase the statistic. What that means is, in a way, like we would need a little less number of sample size in this case. Okay. Cool. So, okay. Actually, for example, this is the quote I found in one of the paper where, like, Google experiment platform head, he said they are not satisfied with the amount of traffic that they are getting, even with the 10 billion searches, because they want to measure such small effect, and they want to finish the experiment at, let's say, in a week or two. They don't want to extend the experiment. So within that period, it is much harder to measure a very small improvement, which might mean increase in revenue by millions, but even the Google are not able to test. So that's why we need this variance reduction technique. And the way to do is to reduce the population and the control variance. And how do we do that? We are using the common variables that are affecting the performance. We are taking the correlation of the metric. Let's go here. We're taking the correlation of those metrics, and then we are subtracting that impact from the actual value. So this is a mathematical reasoning behind this. If you see, basically, so we are short on time. I will just skip on it, but I will share a link to the paper that is just found. And basically, the idea is, if we can represent the equation in this way. We take expectation of this; these two terms cancel out, and the expectation of the final value that we're getting is similar to y bar. But if we, instead of expectation, if we go for the variance, we get this variance in this form. And here the theta, this variance, this becomes a linear equation if you look at in terms of y and x. And using alternative least square, you can find the variable value of theta that minimizes this. And in this case, the theta is covariance of y by x divided by variance of x. And using this, we can reduce the variance of the final output. I will just go to show you and like how it works. And we will share the notebook link in the slide so that you can again go into the expert on it. Right. Yeah. For example, we are simulating, we are testing for 1,000 users. We are dividing the users into 50%. You are dividing the users to control and 50% to treatment. Let's say the control mean is 50. The lift that we are introducing is 5. And let's say within the experiment, there are some random variables that are at play, and they are like compared to before the experiment. If you compare it to after the experiment, there is some random variable that are impacting both control and both treatment. So in this case, if you observe here, so what I've done is just show you one line specifically. Yeah. So for simulating post-experiment data, what we have done is we have taken the prior data, and in case if the treatment is set, like we want to introduce treatment, we are introducing the treatment lift. in case if we are not, if the user doesn't fall into the treatment bucket, we are just adding a random noise. And we are adding this random noise both to the treatment and control. Cool. What this gives us is basically like prior to the experiment, if you look at it, our mean was 50, our standard deviation was 10. So like variance is the square of standard deviation, which is 100, and the mean is 44. Let's say we added a lift of 5. Our treatment matrix increased by 54. And because we introduced a variance of 5 also, basically the random standard deviation, its variance, the square is 25. So 25 into 100, like it will be near to 125. Cool. But if once we apply this Qpid application, what we observe is for the same data, the variance that we are getting has reduced. Like compared to this data, the variance has reduced. So what this would mean is using this data, if we do the same post-experiment analysis, we get a much higher significance. Cool. Yeah. Now getting back to some rule of thumb, basically this was mostly on the analysis part. Going back to the rule of thumb, these are rule of thumbs basically observed in the industry after years of dealing with the experimentation. So shifting clicks is easy. The first thing is like when you are doing an experiment, one thing you have to remember is, for example, you are on Amazon, you made a feature specifically for TV, and you are recommending TV or like promoting television. What that would impact is basically on the home screen, there is a limited area. So you will be cutting clicks from some other product, definitely. For example, you can test the, okay, if you created this campaign, the sale of TV has increased, but this might impact the sale of other equipment, let's say fridge or something. So basically, shifting clicks from, let's say, one item to another, that is easy, but increasing the overall engagement is hard. Second rule of thumb is speed matters a lot. So for example, if you can test the experiment within 2 days, then you can do 10 experiments in 20 days compared to, let's say, if you are taking, let's say, 20 days. So basically, if you have a large user base and you use the variance reduction technique, you can conclude your experiment faster. Third thing is avoid complex design. So like the whole idea of A/B testing is to quickly iterate over your, you have a hypothesis, if you test it, get back to the drawing board, create a new hypothesis. So the best way is to like create simple hypothesis, make a minimal viable change that is like that can help you test your hypothesis. And the fourth thing is big wins are rare. Like you may always target, okay, I will increase the CTR from 50% to 55% or 20%, but that is usually not possible. And this is a famous quote by Al Pacino in Any Given Day. Big wins are rare, winning is done inch by inch. So focus on small wins. Like, I mean, of course, big wins are good, but small wins are equally well. Common pitfalls and misconceptions that we're getting. Okay, so for example, you are doing an experiment and you scheduled, okay, you need 10,000 users, and you compared, okay, every day 1,000 users come to your platform, so you will end your experiment after 10 days. So we have this urge to regularly look into the data, see, okay, how the data is doing. Let's say after every day, we're calculating the p-value. And let's say at the day 2 or day 3, let's show you this graph. So this is the p-value, how p-value of experiment varies with the number of days the experiment has been like. So for example, let's say you launch this experiment, and let's say after 2 days, your p-value is this. You say, okay, no, the p-value is low. Let's stop the experiment. So if you take a decision at this moment before getting the complete sample size, you more likely there's a much higher chance that you will end up with a wrong wrong test, because the p-value is not mature, and it will change every time. Like with for example, every day you might find some deviation in the p-value. So it's ideally good to wait till the end of the experiment to look in the data. If you're keen on looking into the data, just don't take any decision. Okay, in day 2, if you observe a lower p-value, let's just don't take a decision. If on a day 5 you observe, okay, now the result looks significant and it is better, again, don't take any decision. This is the delta, and this is the p-value corresponding to that. So again, don't take. And if you peak, at least don't make any decision based on that. Let the experiment finish, let the numbers come, and then you have third thing I want to discuss is basically some misconceptions on the p-value and the confidence interval definitions. So the p-value is the probability that the hypothesis is true. For example, if let's say this is the statement that people more often not believe, that if the p-value is 0.01, then the null hypothesis has only 1% chance of being true. This is not the case. P-value assumes that the test hypothesis is true, and what it says, because you get a very low p-value, what it says is the result that you are getting is very extreme if it came from the null hypothesis. So it is just saying that the extremity of the data that you observed is very high if the null hypothesis was true. Second misconception is on the 95% confidence interval. I think we already touched upon it, that it is believed that if you get 95% confidence interval, then there is a 95% chance that the true effect will lie in that range. It is not true. Basically, what it means is if you run 100 experiments and create confidence interval for all of them, for 95% of the experiment, the true value will lie in the confidence interval. We'll go to the question and answer in just a slide or two. Third misconception, alpha and beta misconception. Basically, like this is this industry standard that alpha should be 0.05 and beta should be 0.2. These are not golden rules. They can be and should be changed based on your problem statement. For example, let's say you are testing a new drug. The negative impact of it can be pretty high, right? If you let's say you created a new drug and you launched it, and if it lies into the false positive scenario, then it will have an impact. So, like in this case, we can use a lower false positive. Let's say we can use alpha of 0.01. Cool. For further reading, we have mentioned some resources here. Please, if you have any questions.
Kapil, I'm answering the question answer in the chat, sir.
Okay, a link to the AB simulated notebook. We have mentioned in the notebook. I will just
So, all right, guys, I hope you guys have filled in the feedback poll. If not, I request you to please fill in the poll about feedback, as it helps us to conduct more such sessions. If you wish to conduct a webinar or are facing difficulty in registering, connect with us at whatever the link is given in the chat section at editor@analyticsvidya.com. Also, the recording of the session that was conducted today will be available in 1 or 2 days on our YouTube channel. The link is posted in the YouTube and in the chat section. We'll post it again. Till then, is there anything left to ask or to cover extra?
Go to the second last slide. Okay. This one. Which slide? Any questions?
Also, Kapil, so if you could just share the Jupyter this thing,
Yeah,
the
yeah.
notebook thing, so that we can share it with the
yeah,
other
I've
parts.
shared the link in the chat, and the link is also present in the PPT.
All right, sir. All right. Got it.
This is the notebook.
Yeah.
So yeah, go ahead and play with the simulator, and that would be the best way to learn.
All right. Thank you so much, sir. This was really a very insightful session about the A/B testing. I'm sure our the people who have joined might also have learned a lot of things to take away from here. So guys, we'll be back with another session of the data in like next 20-25 minutes. The link is in the chat section. Till then, bye bye and keep learning.